Hey everyone, and welcome to this explainer. Today we're diving into the incredibly fascinating world of simple vectors and transformations. Think about it, we use the language of movement every single day, right? Whether we're mapping out a summer road trip or watching a character sprint across a video game screen. But how do we actually define that movement mathematically? Well, to wrap our heads around the modern mathematical language of movement, we've got to look back at some historical rule breakers who literally shaped the numbers we use today.
Okay, let's jump right in. Here's our roadmap for today. Number 1, the math renaissance. 2, understanding transformations. 3, decoding column vectors. 4, direction and negative vectors. And finally, number 5, adding and subtracting vectors. Let's do this.
Section 1, the math renaissance, rebels in numbers. So before we start sliding geometric shapes all around a grid, we really need to appreciate how foundational arithmetic and algebra even made their way to Europe in the first place. Because honestly, it wasn't a given, it was a full-on revolution. Just look at this guy right here. This is Leonardo Pisano, though you definitely know him better as Fibonacci. Living from 1170 to 1250, he played a massive, absolutely crucial role in math history. He essentially introduced new arithmetic methods to Europe, bringing in things like the decimal system, algebra, and the lattice method of multiplication. But here's the thing, he didn't invent these in a vacuum. He studied the incredible work of Hindu, Persian, and Arab scholars.
Now, you might actually recognize these numbers. Yep, it's the famous Fibonacci sequence, where each number is just the sum of the two right before it. He noticed this specific pattern occurring naturally all over the real world. But what makes Fibonacci such a true pioneer of learning is his transparency. In the introduction to his famous book, Liber Abaci, he explicitly credits the Hindus for the mathematical foundations he was bringing over to the West. Pretty cool, right?
But while Fibonacci brought these numbers in pretty smoothly, others faced some intense friction. Take Girolamo Cardano, for example. He was a brilliant mathematician of the Italian Renaissance. He published Ars Magna, or Great Art, which was literally the very first algebra book written in Latin, and it introduced calculations for solving cubic equations, a real game changer. But the powerful Roman Catholic Church at the time? Yeah, they were pretty resistant to change. Because Cardano also dabbled in astrology, the church definitely did not approve, and he was actually charged with heresy in 1570. Crazy, right? Though he was eventually found innocent, he never published another work. It just goes to show you that pushing the boundaries of math used to be a very dangerous game.
Section 2, Understanding Transformations, the Language of Movement.
All right, now that we've got our arithmetic foundation, shout out to those Renaissance rebels, let's transition over to modern geometry. How do we describe moving an object from one place to another without changing its shape or size? Well, in math, we call this a translation. And a translation is essentially just a sliding movement. Imagine taking a flat shape on your desk and just sliding it directly to the right, or maybe pushing it diagonally up toward the top corner. It doesn't spin, it doesn't grow or shrink, it just slides. But simply saying slide it up and to the right isn't precise enough for us. We need a highly specific mathematical tool to describe this exact slide.
Which brings us to Section 3, decoding column vectors, x and y directions. What's really cool here is how column vectors perfectly organize and describe these sliding movements on a grid. They give us the exact mathematical coordinates for our slide. So, a column vector basically looks like two numbers stacked on top of each other, wrapped inside brackets. It's elegantly simple. Step 1, you look at the top number. This tells you your movement in the x direction, so exactly how far you move horizontally, left or right. Step 2, you look at the bottom number. This is your movement in the y direction, meaning how far you move vertically, up or down. Top is sideways, bottom is up and down. Easy. Oh, and real quick, if you're finding this helpful, make sure you subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations.
Okay, let's look at some examples from our source material to see this in action. Take vector AB, written as a 1 over a 3. This means that from point A to point B, you physically move 1 unit in the positive x direction, so 1 step to the right, and 3 units in the positive y direction, so 3 steps up. Now check out vector CD, which is 0 over negative 2. The 0 on top means there is absolutely zero horizontal movement. None. You aren't moving left or right. The negative 2 on the bottom means you just slide 2 units straight down. Makes perfect sense, right?
Moving on to Section 4, direction and negative vectors, reversing the flow.
We just touched on negative numbers a second ago, which brings us to an absolutely crucial concept, direction. Vectors represent not just distance but specific targeted pathways. And this brilliantly illustrates what happens when we reverse that pathway. Over on the left, we've got vector A, which is 2 over 5. That's 2 to the right, 5 up. But what if we want to backtrack that exact same path? We use a negative vector. Vector negative A over on the right is negative 2 over negative 5. See what happened? A negative vector simply reverses the mathematical signs, which effectively reverses the physical direction of the movement. You go 2 left and 5 down. You're basically walking backward.
Okay, before we start actually doing math with these, we need to quickly go over the notation rules. Vectors can be named by a single lowercase letter, like A or B, or by 2 capital letters representing the start and end points, like AB, with a little arrow drawn right over the top. That arrow is vital, guys. It indicates the exact direction of the translation, from point A to point B. Oh, and here's a pro tip for your own geometric calculations. If you're writing single-letter vectors by hand, you should always underline them to show their vectors. Obviously, you can't easily handwrite in bold font, so the underline is your best friend here.
Section 5. Adding and subtracting vectors. Combining movements.
All right, let's see how all this builds, transitioning from single movements into full-on vector arithmetic. What happens if you slide a shape and then slide it again? Well, our text states, the translation represented by vector A followed by vector B can be written as a single transformation A plus B. Visually, if you were to draw this out, you'd connect the vectors diagrammatically from head to tail. You take the first slide, mark exactly where you end up, and then start the next slide right from that new spot. The overall journey from your very first starting point to your very final ending point is your combined vector.
And numerically, adding vectors is remarkably simple and, honestly, deeply satisfying. You don't need any complex formulas here. You literally just add the top x values together and the bottom y values together. Check out our table. Vector A is 2 over 5. Vector B is negative 3 over negative 2. For the top x value, 2 plus negative 3 equals negative 1. For the bottom y value, 5 plus negative 2 equals 3. Boom! Our resulting single transformation is negative 1 over 3.
So you're probably wondering, what about subtraction? Well, the absolute crucial point to remember here is that vector subtraction isn't some completely new, complicated rule. It's simply the addition of a reversed negative vector. Step 1, realize that A minus B is exactly the same thing as A plus negative B. Step 2, just reverse all the signs in vector B. And step 3, add those x and y components together, exactly like we just did.
Let's actually test this out with a quick challenge from the source material. I want you to mentally map this out with me. How do we calculate vector A, which is 2 over 5, minus vector B, which is negative 3 over negative 2? Remember our steps? We need to turn that minus into a plus by reversing the signs of vector B. Have you got it in your head?
Okay, let's walk through the final solution together. We start with 2 over 5. We're subtracting negative 3 over negative 2. Let's look at the top x line first. 2 minus negative 3. Subtracting a negative acts as mathematical addition, right? So 2 plus 3 is 5. Now for the bottom y line, 5 minus negative 2. Again, that double negative becomes a positive, so 5 plus 2 is 7. Our resulting vector is 5 over 7. It perfectly maps the net movement. Awesome job!
We've covered some incredible ground today, from the rebellious mathematicians of the Renaissance to mastering the addition and subtraction of column vectors. But I want to leave you with this final thought. We've mastered translating flat shapes on a grid, but how do these exact same foundational sliding movements help us map complex physical forces like gravity, wind speed, or architectural load in the real world? Think about that as you look at the physical forces all around you today. Thanks so much for joining me on this explainer. Keep questioning the math behind the movement, and as a final reminder, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Catch you next time.